Hello, everyone. Welcome back to this quick introduction to number theory. What we're going to do today is talk about congruences. So congruences are something that you are actually already used to because we all use clocks. We know clocks, not digital clocks, but like regular analog clocks. And when we compute hours on a clock, we're using congruences. So let me show you what I mean. So for example, if it is 8 o'clock, suppose it is 8 p.m. What time will it be after 5 hours? So how do we do that? We start here. So suppose it's 8 o'clock. And there's going to be 5 hours are going to go by. So it's 1, 2, 3, 4, and 5. And we know it's going to be 1 p.m. So we're going to go from 8 p.m. To 1 a.m. in fact, but it's 8 o'clock, so it's going to be 1 o'clock after 5 hours. So the answer is that it will be 1 a.m. Okay, so how do we compute that? What is actually happening when we do that, we actually in our head, we compute 8 plus 5, which is 13, but we automatically convert that to clock hours. So we automatically see that, well, after 12 is 13, but we just call that 1. What we are actually doing is subtracting from 8 plus 5. So now what we do is subtract multiples of 12 until we're back in a number between 1 and 12. So what we are actually doing then is actually doing long division by 12. And keep the remainder. Right? So what we've actually done is 13 is 12 times 1 plus 1. So discard these multiple of 12 and just keep 1. So that is how we computed that 8 after 5 hours, after 8, it will be 1 a.m. in this case. What about, let's do some other examples. So how about if I want to know what it will be if it's 8 o'clock, what time will it be after 27 hours? So the answer is that I can take, first of all, 8 plus 27, that is 35, and then do long division. So this will be 12 times 2 plus 11, and then forget about the multiples of 12, and this tells me that it will be 11 o'clock when those many hours have gone by. If you actually want to keep track of AM and PM, so if I want to know PM and there are 27 hours go by, then actually what I need to do is keep track of my hours in a 24-hour clock. So so if we want to keep track of AM and PM, what we are going to do is do long division by 24 instead. So so 8 PM plus 27 hours, then what I do is do like before, 8 plus 27 is 35, but now divide by 24, that's 24 plus times 1 plus 23. So it will be the 23 hours, which in a 24-hour clock that is the 11 p.m. Okay, so that is how we use congruences in real life. And in general, we're going to do this for many other purposes. And here's how we define congruences. So here's the definition of a congruence in number theory. So let this paper here, let m bigger or equal to 1 be an integer, which will be called the modulus of the congruence. We say that a and b, two integers a and b, are congruent modulo m, and if their difference is divisible by m. In other words, we actually write this, the congruence of two numbers. We say that a and b are congruent with that triple line equality symbol, if and only if their difference is divisible by m. Remember that this bar here means divides. So if a minus b is divisible by m, then we say that a and b are congruent to each other. Okay. So sometimes, by the way, this you will see also written a b modulo m. So some authors will skip the mod part. So let me show you some congruences, some examples of congruences. So for example, 35 is congruent to 11 modulo 12 because, well, how much is 35 minus 11? That's 24, and that is 12 times 2. So yeah, so 12 divides the difference, 35 minus 11, and therefore that satisfies the condition that 12 divides 35 minus 11, so 35 must be congruent to 11 modulo 12. And that's why that hour of 8 plus 27, which was 35, was congruent to 11 in the clock. So that's the 11th hour in a clock. How about, let's say, for example, 47 is congruent to 23 modulo 24, because 47 minus 23 is 24. So yeah, so 24 does divide the difference, 47 minus 23. This is for all integers. This definition works for all integers. So I can also say that minus 3 is congruent to 8 modulo 11 because minus 3 minus 8, so the number minus 3 minus 8, that is minus 11, and minus 11 is 11 times minus 1. So yes, so 11 does divide the difference, minus 3 minus 8, and therefore minus 3 and 8 are congruent modulo 11. Why are congruences useful? Well, they're useful because they satisfy a number of properties. And one of the properties that is key here is that computing things with congruences is very efficient, because when I have to do large operations in integers, but I'm only interested in their congruence properties, I can first reduce the numbers and then do those operations. Let me see if I can explain what I mean with this proposition. So if you have a number, A1, so let A1, A2, B1, B2 be integers. Let me write let instead of if here. And then if, so A1 and B1, suppose those are very large numbers, and A2 and B2 are the reductions modulo M. Okay, and let M be some modulus, then if A1 is congruent to A2 modulo M, and B1 is congruent to B2 modulo M, then three things happen. First of all, if I have to add A1 and B1, remember that these would be some very large numbers that I'm trying to add. I can first reduce A1 and B1 and then add the reduction. So A1 plus B1 is the same as A2 plus B2 modulo M. If I have to multiply two numbers that are very large, A1 and B1, but at the end of the day, I'm only caring about the reduction modulo M, I can first reduce A1, I can reduce B2, and then multiply them together, and I'm going to get the same answer. And if A1 is congruent to A2, if I want to compute a large power of A1, I can reduce A1 first and then take the power modulo M. Okay, and this is true for all n bigger or equal to 1. So that is very important in the applications, and that's why many cryptographic systems are based on congruences, because I can do many operations very quickly and very efficiently with congruences. So for example, suppose I want to compute 35 plus 47 modulo 12. Then what I can do, instead of adding those two very big numbers that have 2 digits, instead of those, what I can do is actually reduce those modulo 12. I had already computed in the previous page that 35 is 11, and 47 is actually also 11. So that is 11 plus 11. But those are also 2-digit numbers. So instead of doing that, I'm going to switch them again by something they're congruent to. You see 11 is congruent to -1 modulo 12. So this is -1 plus -1. And that is very easy. That's just -2. And -2 is congruent to 10 modulo 12. Okay, so the solution is 10. You see that the numbers modulo 12, so numbers that are congruent modulo 12, so for example, if I have 11, so let me write here a note that 11, if I add 12, it will be congruent to that modulo 12. So 11 plus 12, that will be 23. Those are congruent modulo 12 because they differ by a multiple of 12. And similarly, 11, if I subtract 12, those are also congruent modulo 12 because, well, 23 minus 11 is 12. Because 11 minus -1 is 12. So 12 divides those differences, so they have to be congruent. In general, if you have any number and you want to consider what numbers are they congruent to at modulo M, you can add multiples of M, you can subtract multiples of M, and you get all the numbers that are congruent to that one number modulo M. Okay, what else can I do? Using the properties we just discussed, of congruences, I can suppose I want to compute what is the residue modulo 12. So what is the remainder of 47 to the 23rd power when I divided modulo 12? Now that is a gigantic number, 47 to the 23rd power. So I do not want to expand that first in decimal and then divide by 12. That would be very time consuming. But what I'm going to use here is that 47, I know is congruent to 11, which is congruent to -1 modulo 12. And that's going to tell me that this is the same as doing -1 to the 23rd power modulo 12. But -1 to an odd power is -1, and -1 is congruent to 11 modulo 12. So what this tells me is that 47 to the 23, when I divided by 12, the remainder is 11. So you see, I can do some, at least we'll see other methods to compute powers very quickly using congruences. But in here, I use this trick to come up with something very, very quickly. Okay. The other thing we can do with congruences is the following. So here's an example. Solve, if possible, or let's solve in integers. Let's say find an integer x, if possible, such that 3x is congruent to 1 modulo 7. So we're going to be able to solve some equations in one variable or two variables using congruences. We're going to use some of the methods we learned in the previous videos. Why are we interested in this? Here, 3 is, we're looking is for the multiplicative inverse of 3 modulo 7. So x here is the multiplicative inverse of 3 modulo 7. Because x is the number such that 3 times x is 1. So that is, x is playing the role here, not exactly because it's going to be an integer, is going to be playing the role of a third in modulo 7 arithmetic. Okay, so that's interesting that, of course, there is no integer such that 3 times an integer is 1, but there is going to be an integer such as 3 times an integer is congruent to 1 modulo 7. So I do have multiplicative inverses modulo 7, while I do not have a multiplicative inverse of 3 in the integers. I have it in the rational numbers. Okay, so how do we do that? So again, what we're trying to solve is 3x is congruent to 1 modulo 7. So let's see what this means. What this means is that I want so find x, an integer, such that 7 divides 3x minus 1, the difference of 3x and 1, right? So this will happen if and only if I find x and y integers such that 3x minus 1 is a multiple of 7, which I'm going to write as 7y. So if and only if there are integers such that 3x minus 7y equals 1. And this right here is what we called in a previous video a Bezout identity. And we learned how to solve it, how to find the solution using the GCD of 3 and 7. So what we're going to do is use Euclid's to find the GCD of 7 and 3. So Euclid's algorithm tells me that what I need to do is 7 is 3 times 2 plus 1, and then 3 is 1 times 3 plus 0. So here is the GCD, and the GCD in this case, this is a very simple case. Then this tells me that 1 is 7. Let me write them in the order that I have the equation up there. Minus 2 times 3 plus 7 is 1. Okay, so that is the solution to the Bezier equation is given like that. So what I found, or if you want to write it as I had it over there, then 1 is 3 times minus 2 minus 7 times minus 1. Okay, so this is x and this is y above. And all I needed actually was x. So x, so if I take x to be minus 2, then what happens? 3 times minus 2, that is a minus 6. But minus 6, if I add a multiple of 7, I get 1. So this is actually congruent to 1 modulo 7. So x works. Okay. So I found that x equals minus 2 works. Let me show you another example of this. So example, solve 10x is congruent to 1 modulo 13 for some integer x. So what we're trying to find is the multiplicative inverse of 10 modulo 13. So what I do is start already with Euclid's of 13 and 10. And I know that's 1, but let's do Euclid's algorithm. That is 10 times 1 plus 3. And then 10 is 3 times 3 plus 1. And 3 is 1 times 3 plus 0. So the GCD is 1, as predicted. And then I can write that 1 is 10 minus 3 times 3. And then 10 minus 3 times 13 minus 10, that is 10 minus 3 times 13 plus 3 times 10. So 1 is 4 times 10 minus 3 times 13. And what matters here is what is multiplying 10. So what this says is that x is 4 here. Okay, so I can take x to be 4, and let's see that it works. 10 times 4, that is 40, and 40 is 39 plus 1, so it's some multiples of 13 plus 1, so this has to be congruent to 1 modulo 13, so it works. So the solution to the problem is that x is 4 works. Any other number that is 4 modulo 13 actually works. So any number that is 4 modulo 13 will work the same way. So if you take, for example, instead of 4, you take 17, 17 also works. All right. So, so in general, what we have is the following, which I'm not going to prove. So, but let a be an integer and m a modulus, then the equation ax is congruent to 1 modulo m has a solution x in integers if and only if the GCD of a and m is 1. So in the previous cases we had 10 and 13, the GCD was 1, so it worked. 3 and 7, the GCD was 1, so it works. But if you have, for example, try to find 3x is congruent to 1 modulo 6, there will not be a solution to that. And moreover, if B1 and B2 are solutions of AX is congruent to 1 modulo M, then B1 is actually congruent to B2 modulo M. So what this means is that, i.e., the solution is unique modulo M, which is always a nice feature. Okay, so I'm going to stop here. This is just the basics of congruences. And then in the next video, I'm going to talk about congruence classes.